I forgot to start recording. We're a little late. We're on the start of the notes, just below the very start. When I looked at leadership, I think I included that like one person. What are you gonna do? All right. Do you have an answer?
Yes.
No.
I have an answer.
Okay, there are two big ones that you have definitely have in your parent function library that have horizontal asymptotes. That's definitely one where you have.
How was I going to say no?
No, where you would have, no, it's good. Where you would have to make it decay rather than grow. Okay. Esther, you have an idea? Give me a shout. Give me a starter. Just basic, just the name of the function. Don't worry about the people. What kind of function is it? It's got meaning. Exponential. Okay. Exponential is good. Is this exponential growth or decay? Decay. Okay. So we know that one possibility is this. How do you make it decay? What in the equation causes it to decay rather than grow? The E is constant, so that's not it. What else? Decay. Decay. Decay is what it's about. In order for it to decay, K must be negative. Okay. So anything along the lines of what does A naught need to be? If the rate starts at a third, so at time zero, the rate is a third, then what's A naught? 1/3. Okay. So 1/3 e to the, now it doesn't say how it decays. So I would say anything negative here, if you just said that, cool. If they give me how fast it decays, then I can nail that K. But I can't know unless they told me, how it's decaying. I couldn't do any better. You with me? Are you with me? Okay. So that's a common horizontal asymptote graph. There's another common horizontal asymptote graph, which I would be giddy with joy if you actually knew the name for it. But maybe you could just give me what's a function that approaches a horizontal asymptote besides that. You should know. You've done it since Algebra 1. What's a function that has a horizontal asymptote and a vertical asymptote? Yes, ma'am. What? Yes.
No, I was not.
Yeah, you did. No, you definitely raised your hand. Yep, that's your hand raised right there.
I was imagining what it would
Yeah. What is that?
No, natural law.
No, natural log looks like that. They try to. No, definitely not.
Is this?
Yeah. This guy? Anybody know the name for that? 1 over x, the rational. It's called two things actually. It's rational function because it's got a ratio in it. It's also a hyperbola. So that has a horizontal asymptote behavior. This would normally have an asymptote at 0, so 1 over t would wash. We'd have to shift it over a little so that at 0 it was there. So we probably want to maybe shift it over 1. Sound good? So maybe 1 over, how would you shift it? Left 1. Minus 1 or plus 1? Minus 1, it feels like that would break down at positive 1. You want it to break down at negative 1. So it needs to be t plus 1. Do you agree that that would be cool at 0, be cool at 1, but would have a vertical asymptote at negative 1, yes? Now it doesn't have the problem, or it doesn't have the thing of at the axis it's a 1/3. How would I cause that to happen? At 1/3. I could, so just focus on this. We want when time equals 0 for the amount or the rate to be 1/3. So if I just stuck a 1/3 there, wouldn't at time 0 we'd be good to go? The rate's 1/3? Okay, so there are two possibilities. This one or this one. Either one, they would both accomplish the two goals, which is at time 0 the rate is 1/3 and it decays. All right, that's math modeling. You take all those library of functions you know and try and fit a real life phenomenon on top of it, all right? Which one do you want to use for the rest of the problem? Oh. E2. Okay, that integrates well, so good idea. All right, now, I think you'll agree that because this rate varies, you cannot just do one rate times time calculation. The rate is constantly changing, so I can't just do 1/3 of a problem per minute times 10 minutes like that, because the rate isn't 1/3 of a problem per minute. It's constantly decreasing. So we have to break this into infinitely many calculations like that, yeah? If the rate is changing, then you have to use many calculations. So the amount, the number of problems, I'll let n equal the number of problems done at time t minutes. The total number of problems done would be a ton, an infinite sum of many rate times time calculations. We'll say we're going to use the, actually, time 1 to time 2 of the e, although either one. You with me? All right. Now, building off, just trying to tack on to what we talked about last week, if I ask you for an integral defined function, then that means give me a function that gives you number of problems from 0 up to any one point. The idea being that all these rectangles represent rate times time calculations. And so all these rectangles really added equal problems done. You with me?
Yes.
If I wanted to know how many problems done from 0 up to any number, then the region would start at 0 and go up to some t. So if I wanted number of problems done at any time, I'd say just calculate the area from 0 up to whatever time ending point you want, and you're good to go. Now remember, we can't use t again here because now t represents the end point, not the shape of the curve variable. So you create what's called a dummy variable here. I'm going to use x in this case because x is nowhere else in this problem. That's an integral defined function that represents the accumulation of problems done from 0 up to some time. You follow? Okay, let's practice this in your calculator. Your calculator, this is one of those awesome things where you guys are so lucky to live in when you do, because your calculator can do this. So you get out your calculator, and let's type in the graph menu the integral defined function. So give yourself a definite integral in F1. And I'm going to actually be switching stuff around a little because the integral expects you to do it in terms of t. I'm actually going to be writing this a little funky, and I apologize, but the calculator is what it is. We're going to go from 0 up to endpoint x, but in my mind, that's the ending time. And here I'm going to do the function as a function of t. But again, on my work, those are actually opposites. You follow me? The calculator wants it to be a function of x. So go 1/3 e. I just keep forgetting this, but remember e has to be this e, not the catalog, or this e doesn't flush. So make sure you use the function e. To the, what do we say, negative x? Or negative t rather, right? Okay. T. And boom. Something like that. You with me? Okay. Now, you might be thinking about, first of all, Wait a second, I thought it was supposed to decay. Why isn't it decaying again? Yeah, I'm not graphing here the rate function, which would decay. If I graph the e function, it would be that decay shape. I'm graphing the integral function, which is the accumulation of problems. So doesn't it make sense that the accumulation of problems is growing with time? Right? It is getting bigger. All right, so now that we have that integral defined function, we could find any question. So for example, this question says, given an integral to function, find integral defined function of problems done as a function of time. Boom, how we've done that. Find how long it takes Joe to get his problem set, 25 problems done. How would you answer that second part of the question? When does he get 25 problems done? What is 25 problems in this equation? Empty is number of problems done. So we want to find when this equals 25. And we could actually do that paper and pencil because we can integrate E pretty well. So we could actually solve that if we wanted to, paper and pencil. But let's use our calculator. So how would you use your calculator to solve that question? We got the graph of this side. Tell me what I should do. Graph, say it again. Graph 25, yeah. We want to see where that meets 25. Now you can see that we're nowhere close right now. So let's go, and I don't even know if our model's any good. We'll see, I guess. This could take a while. Oh, my model was more like, this is going to take a while. Do you mind if I change our model a little bit? Because that's going to take probably years to get it done. Let's change our model. You'll see. It's exponential e to the negative t is going to be really, really, all right, you'll see. Never mind. It's going to take a long time to get. Right now, you're at 10 minutes, and you still haven't even done one problem, okay? So exponential, this goes to kind of, I should have helped you a little. Let's go, can we change our model to negative t over 100? Because exponential growth and decay is super duper powerful. We need to tweak it a little bit because otherwise you're going to be working on your problem set till you're 85. All right, so would you go to your function and change it to negative t over 100? Just to tweak the model a little bit. Okay, now I know that feels like it's almost linear, but you see if we'll zoom out enough, it'll be cool. Would you change your window to, oops, let's go 0 to, at most this should take you 150 minutes for a problem set, right? And we want to go y from 0 problems done to 25 problems done. Let's go a little higher, so 30. So 25 is not the very top of the window. Are you with me? All right. So I changed my window to 0 to 150 on x, which is minutes, and 0 to 30 on y, which is problems done. I didn't do it at 25 because I wanted to see the 25 inside the window, not the top. You with me? Mm-hmm. All right. So then, now to find that solution, how do we find it? Menu, analyze graph, intersection point. Oops, or not. Oh, shucks. Ah, yeah. I'm having trouble doing this on the smart board. Okay, so set a window, and did you get something like 138.629? Okay, interpret your answer then means time it takes, time to finish, to do 100 or 25 problems is 138.629 minutes. That's painful. That's 2 hours and 18 minutes, yeah? Hopefully it doesn't take you that long. Okay, ready?
No.
That's a little long. What kind of model should I probably have used instead? Instead of e over negative t over 100, maybe twice as fast as a rate, so maybe negative t over 200, something like that. You tracking? Okay, let's go to another integral application problem, physics style. Joe pushes a snowball through the snow. The force required varies with distance from his starting point. That makes sense. As the snowball grows, the weight of the snowball will accumulate, and you'll get more force required later on. So if the force required is 2x newtons, find the amount of work required to move the snowball 7 meters from the starting point. What is force? Or work, sorry. What is work? Force times distance. In this case, though, we're doing lots of little accumulations of changes in position, so it's more like, instead of delta x dx, what's the force? Hi. How you doing? Sounds good. All right. So the force function is what for this problem? Oh, wait. Alan. I have been fourth out. Okay, should I just give him something? That's all right. As long as they don't expect it until the end of fourth. Okay. All right. So the function is 7x, yeah? From where to where? Now those limits of integration represent x range. So what's the x range?
Why is it
7x from, oh, I have no idea. 2x, sorry, thank you. Good critical thinking, lady, you're on the game. Okay, 2x rather from 0 to 7, so the range of the integral is from 0 to 7. It is x squared from 0 to 7. That's 49 minus 0. So our answer is 49, and what are the units for work? Joules. Assuming they're newtons and meters, the units are joules. Are we cool? They won't play with you on the units. They'll give you newtons and meters. Are we cool? Those are easy. Those are the ones in the book. Now, let's try another one in the book. Another thing that accumulates or changes as you go. If I attached a garage door spring, have you ever, I don't know if you've ever worked on a garage door, but those suckers are heavy. Okay? If you attached a garage door spring or any kind of spring to a wall and gradually pulled out, would it be the same amount of force at all times? No, it would get harder and harder as you get further and further from the wall, yeah? Now because of that, when you go to stretch a spring, that's a calculus problem. The work required is going to have to be the accumulation of many force problems because the force will change as you get further and further away. Now they will always give you the spring constant. For a spring problem, force equals some spring constant K times the x at which you're at when you're pulling, okay? They'll give you the spring constant for each case. In this case, the spring constant is 7. So the force will be 7x. The spring constant K times x times little changes in motion. You will still have to say, all right, from where to where? Its resting position to 1 meter longer would be from place 0 to place 1. The antiderivative of 7x is x to the 7th. Say what? What's she talking about? What's the antiderivative of 7x, back row? 7 halves x squared.
What did I say?
So that is 7 halves. That still works, so it is joules. Okay? Okay. Last but not least. Okay. Just so you're clear, integrals are used in a ton of fields, so I can't get every possible use of integrals in these notes. But one that I felt the book didn't have, that you do use integrals all the time for, that you, even the honors people, might not have seen, is population density. Okay? So economists, sociologists, city planners, civil engineers, they're all concerned with population density. There's a huge application, or if you do applied mathematics, traffic flow, those people are usually math people, okay? If you want to be an applied mathematician, that might be someplace you get a job.
Yes, that's what
The basic idea is that there's usually a part of the city that people want to live around, whether it be downtown, because that's where their job is, or lakes, or beaches, mountains. And because of that, density varies over a place. Now that makes it hard to talk about how many people live in a certain place without just straight up counting. You'll then often use calculus to talk about how many people live in an area by using population density, all right? We'll give you a couple examples. We'll do one together and you'll try one. A certain beach, perfectly linear. Here's the water. Okay? Extends for 5 miles. The population density can be modeled by that density function. Now that's a decaying exponential function, and the density would decay with distance from the beach. So real close to the beach, it would be very dense, and as you get further and further away from the beach, it gets less and less dense because people want to live by the beach, all right? So the greatest density is by the beach. X is the distance from the beach in miles. How many people live within 2 miles of the beach? Therefore, we're really trying to say how many people live in that area. Okay? Now, think, I beg you, think units. If I were to talk about the density, what are the units on density? People per square mile. Okay? All right? Now, we want to know how many people live in a certain area. So to get people, we want the number of people. In order to get people out of that, we have to take that density and multiply by miles squared. Only by multiplying by miles squared will we get people, yeah? So what do we have to multiply the density by? Miles squared, what do you reckon that is? Oh, geez Louise, a pre-algebra kid could answer that. If you get an answer of miles squared, you probably are measuring thank you, area. Yes, kid. Area.
How we've done the trick.
Okay? Now, I can't just straight up do this function times area because this function is not a constant. It's varying. So that's what we're talking calculus here. Your thought process should be, all right, I want to make this product happen, but one of the factors changes. And if one of the factors changes, you need to make many calculations and sum them, and that's what screams integral. Okay, that's how you answer the question, when do I use an integral? Or when is it an algebra problem? If one of the factors changes, it's an integral. So we're going to say n is the accumulation, of many density times area calculations. Now, each of these little rectangles has a totally different area, or density actually. What are the areas of each of those little rectangles? What's the area of each rectangle? Dx is perfect. Is dx this distance or this? This guy?
Yeah.
Yeah, this guy. This guy, what is this guy? Always. It's always 5. Okay? So we would take that and multiply by 5, and we want to do all those calculations from where to where? 0 to 2. We want to know how many people live within 2 miles of the beach. That means x goes from 0 to 2. X represents the distance to the beach. If you threw that in your calculator, then these will be calculated at 0 to 2 of that guy. Oops. Hang on just a minute. Okay. So the old shift plus 0 to 2. And what are we integrating? 5 times, it was 18,000 what? 585. E to the what power? Negative 0.3. Thank you. X dx. The density would be 139 rounded to the, so if they didn't give me directions, which problems I make constantly don't, the AP would definitely give you directions, but if they don't give you directions, I would strongly recommend you give decimal and rounded, if the answer makes sense. For people, you definitely wouldn't have part people, but cover your tush. Give the decimal and the rounded. So let's go 139,750.
Wait.
139,755 point, what was it, 592?
What?
Is that not what you got for an answer?
Oh.
595 or 139,756 people live within 2 miles of the beach. Okay? How many of you are in AP Stat or took AP Stat? Okay? Those of you who do the norm CDF in your calculus, that's a cumulative density. That's a density function. When you say, hey, the average SAT is, I don't know what is it, 1,200, 1,100? I don't know. Whatever it is. The scores are most dense there. And as you get further and further away from 1,100, they're less dense. So when you do normal CDF, you're accumulating people under the normal distribution up to a certain point. You're doing a density function when you do all those statistics calculations. All right, would you try the next one on your own or with your Math Amigo? Just as in the regular. Okay, try the next one on your own. These are not in the book very often, so you're not going to get any practice. You've got to make the most of it. I'm not a civil engineer. I'm trying to make these up the best I can. This will have a small sub-idea that's important to the calculus also. By the way, while you're working, I will say that the variable that confounds this density function, yes, a lot of people want to live close to a lake or the city or something. Confounds us so as rich people. Rich people say, well, I want to live there too, and I'm going to buy a huge chunk of land so nobody else can live there. That makes the density function harder to write. Okay. Now, I heard somebody say pi r squared, 100% totally understand where you're coming from, except you're totally off on the wrong track. Sorry, my bad. The thing is this, the area of this black ring, don't think of it as a circle, because it definitely isn't. If you think, well, it's more like the ring formula, that makes sense, and that's true, I agree, but that doesn't work either. Instead, think of it like this. This made that. If you snipped it here and straighten it out, you should be focusing on the area of this. Snip and straighten. Okay, that's a little hint. Because for infinitesimally thin circle, it actually straightens out to a line.
Because it's just with the straight. That. No. So 0. So what I'm getting from
Does somebody else not take the test? Me take the test. Are you taking 7th hour soon? Okay.
Mr. Rickman, are you getting these back?
Yes, if I have time, I will give you those.
See the second try.
Okay. Are you ready?
Yeah.
Okay. So first of all, if you're anything like me, I thought, what the heck? How come you said area, and I'm finding the area of that ring? Why are you throwing this complicated idea? Well, it's because this density changes not just from mile to mile, but from foot to foot. And so that area you're trying to find is basically the area of that tiny little, all the people on that little ring. And in terms of changing, it's not really changing. Think of it as changing with distance from the origin, or distance from the center of the lake. So think of it as dx. So we'll talk about this more later, but the idea of straightening it is in your best interest, all right? So wouldn't you agree that in terms of units, we need density, which is people per square mile, and I need to multiply that by area, which is square miles, and that would give me people. Yeah? Yeah? All right. So did you take the density function? Okay. What's the area of this line, which is the same as this rectangle? What's the thickness? The thickness is infinitesimally small. So what should we call it? Dx. Yeah. The thickness of this, the height of that line is dx. It's an infinitesimal. What about the base of that? Circumference, yes. 2 pi r, or in this case, x. Okay? X is the distance from the center of the lake, so the radius is x. So we're looking at 2 pi x dx. That represents the area of any one line. And you have all these infinitesimally small lines. Okay, so you're making lots of little density times area calculations. What are the limits of integration? Be careful. The density of the population of a perfectly circular lake with radius 1 mile. How many people live within 2 miles? So is it 0 to 2? No, what is it? 1 to 3? Yeah. You would start accumulating people not in the center of the lake, 0, but 1 mile from the center of the lake, which is where the shore is, to 2 miles away, 3. So that would be a common source of error. People say 0 to 2, and you'd be saying people are living in the lake. They don't. All right? You never know. You're right. You got your houseboats and stuff like that. All right. So that would be change your model if you have houseboats. That would be cool. Well, good point. All right. So you print that out, and there's your answer, and you would give a decimal, then a rounded number to the nearest people. That is that. So what was this lesson about?
It was about population
Using integration. Yeah, and you can be used in a lot of ways. Using integration. Okay. Cool. Is this the oldest thing you have? Okay. I had a key. It was not. I had a key online, so hopefully you used it. 8 and 3. Should we do 3 first? Okay. 3 was one of the harder ones, I agree. I probably could have. On the AP free response, they commonly give you a picture. I feel like I often don't give you a picture just because you should know how to graph. This one, however, did not graph super pretty princess. Okay, I'll start with the basic sine shape like that. Sine has a wavelength of 2 pi. So something like that, okay? The line, this is y equals x to the first, so it's linear. 1. And what's the slope? Up 1 over pi. So you could say this side it goes up 1 over pi to this point, but more importantly on this side it goes down 1 over pi to this point. So the line looks like that. They say the region enclosed by those 2 curves and the y-axis. On the right-hand side, this is not bounded here, so that would be an infinite area, which we don't do until Cap 2. I'm talking about the region left of the y-axis using the y-axis and the 2 curves. I'm talking that area. All right. Now that we have the area clearly defined, you'll have a better chance of success. How do you find the area between 2 curves? Set them equal to each other to find the intersection. Now I'm giving you a good graph. You can sometimes find the intersection point. They intersect at negative pi 0. And the other point they don't really intersect at, but intersects the y-axis at 0, 1. Yeah? Okay, so intersection points to bound the region. Check. Good job. Now we set up our integral. What is our integral? It's the sum of many rectangles. And the base of the rectangle is dx. And the height of the rectangle is always upper minus lower. What's the upper here? The line or the sinusoid? The line. So 1/2, not 1/2, sorry, 1 over pi x plus 1 minus the bottom sine of x. From where to where? 0 to, not 0, what's negative pi to 0. Remember you're using the x region. The x part of the region is from negative pi to the y-axis 0. Are we cool? Now let's integrate. What's the antiderivative of 1 over pi x? Forget the 1 over pi, it's a constant, so leave it alone. What's the antiderivative of x? X squared over 2, yeah? What's the antiderivative of 1? 1x. And what's the antiderivative of negative sine x? Cosine x. From negative pi to 0. Do I put in 0 first or negative pi? 0. So I have 1 over pi times 0 plus 0 plus cosine of 0 minus 1 over pi times negative pi squared over 2 minus pi plus cosine of negative pi. Wait. This comes out to be just basically cosine of 0. What's cosine of 0? 1 minus, how does this pi stuff clean up there? The pi's cancel, it's positive, a pi cancels, so that's pi over 2 minus pi, and what's cosine of negative pi? What's cosine of negative pi? Negative 1. Okay? 1 minus pi over 2 minus pi is negative pi over 2, yeah? Minus 1. Distribute the negative, combine like terms. 1 minus negative 1 is 2 plus pi over 2. 2 plus pi over 2 is You with me? What else did you say? 8, Lee?
Yes.
All right, 8. These are hard, by the way. They take practice. You will get good at them, but they're one of those things that takes a while. All right. I guess if I really wanted to, I could graph this freaking cube, but I don't want to. So let's pretend that I don't want to get into graphing. I know the shape could look like this, and that is probably like that, but how they relate to each other, let's go to intersection points to determine, what's going on. So intersection points. X cubed plus x squared minus 2x plus 2 equals x squared minus x plus 2. If I combine like terms or get everything to one side, I get x cubed plus or minus x equals 0. The x squareds drop out and the 2's drop out, okay? If I factor out a common factor, I have x times x squared minus 1 is 0. So x times x plus 1, x minus 1. The solutions are -1, 0, and 1. Yeah? Now that would mean then that maybe it would help to figure out where one's on top, one's on bottom. But if they have 3 intersection points, if I put this guy on here to get 3 intersection points, how do I get 3 intersection points? Something like that. How am I going to get 3 intersection points out of that?
Good morning, Devil and Jaguar. Please rise for the pledge of allegiance.
Just a second.
Begin. I
Pledge allegiance
to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all.
Not sure, so let's go to the table.
Council meets today in Mr. B's room. Sign up with your social studies teacher and then come down to the.
Actually, I kind of know, don't I know that the cube has to be more powerful at the far side? So what should be bigger on the far right side?
You are required to meet Mr. Northway in her E100.
Cube should be bigger, right?
Yes.
Are you looking for ways to pay for
So
college?
that would mean the square's bigger here.
Scholarship workshop today during 7th hour. The focus will be on tips to make an impressive scholarship application. Sign up and counseling.
Girls Veterans will have their annual cookie celebration this Friday, December 7th.
So I'm feeling something like that. So in the first region,
Please bring your favorite spring.
the first region enclosed is here, yeah? From -1 to 0. What's the upper?
Please come out tonight to Chipotle on Wadsworth by Coles between 5 to 8 p.m. to support your boys basketball team. Be sure to mention Devil and Boys basketball at checkout. Tomorrow, the boys play Longmont at home. Varsity's at 7 p.m.
Great job marching band in the Parade of Lights. Winter Guard will meet on Wednesday this week from 3 to 5:30. Winter Guard is meeting only once this week.
So if I take the cube minus the square in there,
Last year winning the finals week with the 18th annual Holiday Brouhaha Improv Show next Friday, December 14th. More information will come soon, but be sure to mark your calendars now.
Consider participating in the talk.
and the next region would be the square bigger.
Stop by the Giving Tree display in the middle. Each of the paw or
After that, I would distribute the negatives so you don't have to integrate so much.
free to take an ornament or two and then bring back the unwrapped gift before December 18th.
Senior high students. Juniors, if you are interested in learning more about the college process and getting a head start, please come to counseling to sign up for our junior seminar class for second semester. We will address the college essay, help you understand what colleges are looking for and how to differentiate yourself. The deadline to sign up is December 14th.
Reminder to all school students or all high school students that as part of the Student Advisory Committee, our next meeting is Tuesday during the 7th hour in our E100.
Junior high students. Junior high students who made the second round of the geography meet, we will have the second round competition in Mr. B's
They actually clean up quite a bit.
during 7th hour. If you're not sure if you made it, check with your social studies teacher. Sign up with your social studies teacher and then come to round 2 of the geography meet. That's all your announcements. Have a great day.
All right, we didn't get through 61, but we did, to my mind, The key to this has been up there a while, so I should get the area fund sheet today, please. 1/4. So that's 1/4 plus -1/4 plus 1/4. I'm getting a half here. Cool. All right. If you're lost on all of it, I should see you coming in.
How do you set up?
12? Is there a 12? Oh, yeah, it's a calculator one, right?
Yeah.
Okay. This, you need to zoom out a lot.
Oh,
The reason is e to the x will eventually win. In the window you're probably looking at, x cubed probably looks on top, but the exponential is way more powerful than a polynomial. So you'll need to zoom out. I would change my window maybe to 0 to 10 in x, and maybe 0 to 100 or more in y, because the exponential is going to go super tall fast. Eventually, you just have to do that. One more. Okay? I typically go by powers of 10, so I go to 0 to 100, and that doesn't work because of 1,000. Did you find the intersection? Okay. All right. Yeah, that was the hard part. Have a good day.